from Canada's Perimeter Institute for Theoretical Physics. Welcome to Perimeter Inspirations, classroom videos that investigate the frontiers of science. Join host and physicist Damien Pope of Perimeter's outreach team and leading scientists as they take you on an educational journey of wonder and discovery.
It's a navigational tool used by millions of people every day. With it, drivers know where they're going. Pilots fly planes more safely. It helps construction workers build straighter roads. Farmers plant fields more efficiently. Because of it, golfers choose better clubs. Skiers find faster ways down mountains. The uses for this innovative tool are virtually unlimited. It's called the Global Positioning System, better known as GPS.
So, exactly how does this incredible tool work?
So imagine you're on a field and you wanted to triangulate where you were because you know the positions of things in the distance that you can see. By measuring the direction to one object and another object, you can figure out where you would have to be in the field. Well, GPS is like that, but it's larger. It's in all three dimensions, not only where in the field, but how high, and also it's measuring time. You have 4 satellites, they're sending you signals, and you're measuring accurately where the satellite appears to be and when the signals were sent. And from that, you can figure out where you are on the Earth's surface.
The Global Positioning System is a network of over 30 satellites orbiting 20,000 kilometres above us. They move at a speed of 14,000 kilometres per hour. Each satellite follows one of 6 orbits, arranged so at least 4 satellites are visible from any point on Earth. The satellites constantly transmit signals, easily picked up by anyone with a GPS receiver. Each signal contains information on where the satellite is and what time the signal was sent. Using this information, the receiver calculates its distance from the satellite. This is done by multiplying the signal speed, the speed of light, by the time the signal travelled. The receiver then repeats this procedure for 3 more satellites, narrowing down its location to within a few metres.
To achieve this incredible accuracy, the timing information from the satellites must be extremely precise. So inside each GPS satellite is an atomic clock, the most accurate timing device ever created.
The GPS is so precise, it must take into account a number of subtle effects. Some of these are predicted by Einstein's theory of relativity, an idea that revolutionized our understanding of the universe. This theory includes special relativity and general relativity. Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometres per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers at a rate of 7 microseconds per day.
After Einstein formulated the theory of special relativity, he went further ahead and he proposed his theory of general relativity, which is not only a theory of space-time, but it's a gravitation theory.
Key to Einstein's theory of general relativity is the fact that gravity alters time. Clocks farther away from Earth, where gravity is weaker, run faster than clocks closer to Earth, where gravity is stronger. The GPS satellites are located 20,000 kilometres above Earth, where gravity is much weaker than on the surface. Due to general relativity, satellite clocks run 45 microseconds faster daily. When we combine the effects of special and general relativity, satellite clocks run 38 microseconds fast every day. This may not seem like much, but if uncorrected, all GPS measurements would be off by 11 kilometres daily.
The effects of relativity on Earth are normally 1 part in 10 billion, and so it's an incredibly small effect, and you're used to thinking you can forget it for most things. But when you're relying on how far light travels in a particular amount of time, if you're wrong by even microseconds, then the distances that you're getting wrong are that much larger.
To correct this error, engineers adjusted the atomic clocks inside the satellites, so on Earth they ran slow by 38 microseconds per day. This compensated for the effects of relativity and meant that, once in orbit, the clocks ran accurately, giving us the powerful tool we have today. So, as you see, what began as an abstract theory over 100 years ago is now used in everyday technology. Every time you use GPS, you're using relativity. Whether you're heading out to meet friends, trying to find the nearest movie theatre, or looking for a restaurant in another country, you'll always know where to go using GPS.
So relativity is not just something to study in school. It actually affects daily events in people's lives. Your life.
It's very amazing that after they were developed, they became such an important factor in designing GPSs and navigation systems, and basically we would have been able to do them if we didn't know much about relativity.
On the one hand, you might think of Einstein's theory of general relativity, this theory that space and time are warped, you live in a four-dimensional space-time, you might think that that's the part of physics that's furthest away from day-to-day life, and yet it shows up in this fundamental way in GPS technology, which is crucial to everyone's day-to-day life at this point.
Theoretical physics, closer than you think.